Thanks for the intro. Again, my name is Darrell Knight, and I lead the strategy and innovation team here at FutureOn. A little background on FutureOn. Our roots, as you may know, are in the digitalization area within offshore oil and gas. And we have now developed and established a strategy around the net zero transition to support our operator clients and industry partners as they themselves move to a net zero future. Our intention, though, is to remain energy source neutral. We will continue our investments in digital solutions for oil and gas, but we are now overlaying that with solutions for new energy mixes, combining renewables, especially in the offshore space, like wind, with low or no carbon fuels, with a particular focus on hydrogen production. But we also will remain technology agnostic, supporting multiple cloud providers and an array of technology partners across the ecosystem as the industry itself transitions to a fully digital net zero future. So this presentation has been developed in partnership with McDermott, one of our strategic partners, to showcase some ideas about the concept design of complex energy systems that would include both wind energy and hydrogen transportation scenarios. McDermott is a long-term strategic partner of FutureOn's and uses our cloud-based digital platform, FieldTwin, to develop these digital twin concepts. So today I'm going to be talking about how the oil and gas industry can play a vital role in the coming energy transition with innovative thinking and emerging digital technologies. So the energy transition itself presents three main pillars as represented by these three circles. Firstly, sustainability, which looks at creating and maintaining sort of the balance between the economic, environmental, and social factors that impact the planet and the human race itself. Secondly, the transition to new energy, to transition away from a dependence on fossil fuels to renewables, and ultimately to find new energy sources and fuels to support net zero carbon emissions. And supporting these two key concepts is digitalization, which is effectively the leg that connects them all together, and how we, as a digital software company, believe the climate goals will be realized. While many of the new energy concepts are emerging, we expect them to harness trends in digitalization that have already been implemented in existing oil and gas scenarios. And the footprint and maturity of digital twins is ever increasing across the spectrum of the hydrocarbon-centric energy sector, and is likely to be replicated as this sort of energy transition develops. So technologies like cloud and AI and machine learning already at the heart of digital twins, which support complex data models and used for feasibility studies, concept selection, production optimization, and eventually predictive maintenance strategies. So our position is that these three main strategies, or these three main legs, support are critical to the success of this energy transition world we live in. It is interesting, if you look at this rather unique graphic developed by Rystad Energy, it maps the entire, if you like, the value chain from energy generation through refining, processing, distribution, transportation, and eventually use, and where that use invokes emissions. Really, the main thing about this graphic is it shows we live in a highly complex and multifaceted world where energy is used across all aspects of life. And it's not a simple problem to solve. But what is interesting, if you narrow down the challenges of moving energy from the generation stage, whether it's through drilling or renewables, to producing fuel and ultimately for use case, you can see that hydrogen is very quickly establishing itself as one of the more important key technologies, if you like, or elements within the energy transition. Hydrogen and hydrogen derivatives are being viewed as critical as a missing link between the power generation process and the ultimate end user applications, particularly in industrial use, steel and concrete production, and long distance transportation, aviation, shipping, etc. Other areas, carbon capture and storage, use, and batteries, of course, are also part of that mix. And carbon capture storage is an important transition solution to accelerate the actual carbon being released today into the atmosphere, and plays a vital role. Batteries and rare earth mining of metals like lithium, etc., are also key, but in our perspective, perhaps offer limited market opportunities for the oil and gas industry. But there is no doubt that the demands of a sort of the larger Scope 3 emissions, those emissions produced by the use of hydrocarbons generated by the oil and gas industry, are pushing the industry towards defining and researching a whole set of new low or no carbon fuels, most of which will be based on hydrogen as a primary element of those fuels themselves. And we do believe at FutureOn that there will be a multi-pronged approach to reaching net zero. Decarbonization itself is already happening. Things like electrification of existing oil and gas platforms, and of course carbon capture, as I mentioned, to provide transition to new fuels using blue hydrogen. But ultimately, the transition will identify the new power sources, offshore wind, perhaps wave, perhaps tide, in an offshore scope to help identify and reduce Scope 3 emissions, new fuels. And of course, we focus on the offshore sector. So hydrogen production offshore and nearshore is a major element of that transition. And of course, regional dynamics, where the wind blows, where the sun shines, play an important role in establishing what is a particular company's correct strategy for producing hydrogen itself. I mean, it's already produced today using a process called steam methane reforming, effectively that releases carbon dioxide as a byproduct, but using carbon capture to neutralize that carbon impact allows blue hydrogen to be created. So storing carbon dioxide in existing, already evacuated oil and gas reservoirs, often used as for enhanced oil recovery as an injection gas, is a real solution that exists today. But blue hydrogen is seen by many as a gateway, if you like, a solution to the ultimate color of hydrogen in the end, which of course is green hydrogen. And green hydrogen is called that because it uses a green renewable source to power an electrolysis process to generate the hydrogen. And release oxygen. So it's sort of a very green overall value to the planet. But there will be a mix, and we expect a mix. But the good news is that all these different paths as we go through the timeline towards 2050 all are very clean, and ultimately will produce clean hydrogen. So if we focus on green hydrogen for a minute, and look at the sort of the key components of green hydrogen, where you start with the renewable power source, such as wind power. Water is the starting compound, and then an electrolyzer to provide the processing, storage, and a viable transportation infrastructure. So those are the key components that make up a green hydrogen production and distribution facility. But today I want to sort of focus a little bit on the storage options, and storage and transportation options, because we believe without the right storage strategy, the transient nature of renewable energy, it's not necessarily a reliable energy source, because the wind doesn't always blow and or the sun doesn't always shine. It can be unpredictable and ultimately unreliable. So you have to think of sort of hydrogen as an energy carrier, much like a battery where energy is produced and it can be stored and transported to where it's needed to be. But instead of a battery, in the form of a gas. So storage of this energy is extremely critical to reach the sort of the economic models in the renewable transition space that we live in, and solutions which haven't thought through the storage and transportation component are likely to fail. So there's a couple of options shown on this slide. Option A, the hydrogen produced during electrolysis is modeled to be stored in subsea storage, where some of it can be converted into a fuel cell and then used to power the actual platform. As such, option A is quite suitable to be used as a power source for an existing oil and gas offshore facility, if that facility is to be run by renewable energy like offshore wind, and is actually a viable part of an electrification and emission reduction strategy. In option B, hydrogen can be stored and transported through a custom designed or perhaps repurposed offshore pipeline, where it can be stored in storage tanks on shore, or eventually distributed to end user applications. Within both of these options, there exists the opportunity to store the hydrogen in existing subsea pipeline infrastructure for a period of time, and that same infrastructure then used for transportation. So I'm going to take a deeper dive into this third option, if you like, and work that has been developed by McDermott and present some important implications for the viability of a hydrogen project. So this infrastructure reuse opportunity is significant if you understand how much natural gas pipeline is available over the next 10 years. This is an extract from an OGA report, which covers the Nordic and the UK CS continental shelf regions. Just looking at North Sea specifically here, you see there's more than 5,000 kilometers in existing natural gas pipelines and 40+ platforms in use, which are end-of-lifing over the next several years, and which is an enormous amount of existing infrastructure that will either need to be decommissioned or perhaps repurposed. And I think there really is an opportunity here to repurpose this infrastructure. The cost of decommissioning is seen as a sunk cost and is often something that most oil and gas operators try to reduce or avoid if possible. And this pipeline and existing network infrastructure can certainly be retrofitted to transport hydrogen at a much lower cost than creating a new network of hydrogen-specific engineered pipelines. But certainly the pipelines need to be, a certain length to be economical to store hydrogen. But certainly much of this infrastructure that I'm talking about already sits into this category. And the existing topside facilities themselves can be fairly cost-effectively retrofitted to house an electrolyzer, an HV, high voltage DC unit, water desalination, compressors, and fuel cells to power the actual platform itself. So, if you're combining retrofitted pipelines to transport the hydrogen, as well, you can start to see a picture emerge that can have a real impact in the viability of these offshore hydrogen projects. In fact, McKinsey recently researched the idea of retrofitting existing natural gas pipelines for hydrogen transportation in a report published earlier this year. If you start from the offshore area and feed into onshore and ultimately into distribution pipelines, which tend to have somewhat different properties and structures themselves, you'll see that each stage certainly presents its own set of challenges based on the technical configuration of the existing infrastructure, the ability for, say, the pipeline itself to support, say, different pressure requirements of hydrogen compared to natural gas. But as you can see, in each case, there are expected to be significant cost savings in each phase. And furthermore, since all the embodied carbon, which effectively the carbon that was already released into the atmosphere in the manufacturing process of the steel and concrete, has already been accounted for. So this approach not only helps reduce costs by using existing physical infrastructure, it also reduces the carbon footprint of the resulting hydrogen facility, because those carbon numbers have already been effectively taken into account. But certainly the transportation of hydrogen does come with more complexity than transporting natural gas. And our colleagues at McDermott have a deep understanding of these challenges. To transport hydrogen through pipelines, you need to be aware of the material composition of the pipeline, especially the wall thickness, which is impacted by the operating pressures of hydrogen. You will certainly need more or additional compression to maintain the higher pressure levels compared to natural gas needed to successfully reach the destination. And hydrogen density is almost a third of natural gas. So if you wanted to transport the same amount of hydrogen as natural gas, your flow rate will need to be 3 times that of natural gas. Unfortunately, this high flow rate may cause fatigue, erosion, as well as what's known as flow-induced vibration. So you'll need to factor in these safety calculations. In addition, hydrogen can cause material degradation to the pipeline itself, which will need to be dealt with during any retrofitting. There are other factors to consider, such as loading, free spanning, fracture control, the actual age of the pipeline, etc. So there's lots of value, lots of considerations, many of which are interconnected, and all these considerations do need to be modeled and assessed to determine our overall costing and actual feasibility, which in turn leads us back to creating digital models and a digitalization. So to successfully analyze and track all these moving parts, all these factors, it is clear that you do need some powerful data modeling tools combined with a digital twin to monitor the end-to-end hydrogen production, transportation, and distribution for maximum production efficiencies. So McDermott utilized FutureOn's Field Twin platform. It's a digital twin design platform to develop some of the various concepts. Some of the areas they used our platform for was, for instance, designing and optimizing wind farm layout using a predefined layout grid and implementing their own optimization algorithm, being able to place the high voltage DC platforms, if you like, and electrolysis to convert the HVDC from the wind farm itself to run the electrolyzers to create the hydrogen. The storage capacity analysis, which would need to offset the transient power variations from the wind farm, including utilization of existing infrastructure, like existing pipelines. And then the optimal pipeline design to support the nature of hydrogen as a gas, the pressure and density coefficients that exist within hydrogen. And then further taking into account, as we just talked about, what existing infrastructure, being able to pull in and analyze existing natural gas pipelines to see if they can be used as a possible storage and or transportation facility. Also included in the analysis were various options to develop or modify existing topside platforms, those that might be otherwise decommissioned. So here we have an example of a modified platform specifically for green hydrogen production, modifying the platform to add the membrane electrolyzers as well as the hydrogen storage, some hydrogen storage on the platform itself. And this is an example of a blue hydrogen modification. So the platform is modified for hydrogen storage and the steam methane reforming process, where you would also add in the carbon capture process using an existing well, often used, as I mentioned earlier, for enhanced oil recovery. So being able to model not just the topside and the subsea, but also some of the subsurface infrastructure, such as a well, is an important element. So this short video showcases the entire project, how it sort of comes together within the Field Twin software. As you can see, each element is presented in 3D. Everything has underlying metadata and intelligence associated with it. So it can be easily modeled, and various concepts and what-ifs can be pulled together within the platform to create a compelling presentation of the information. And this is a view of a Field Twin itself, the application, and some of the capabilities, which is currently being used in a project off the coast of Germany in the North Sea, project called Aqua Ventus, focusing on an island called Higlia Land in the North Sea. Zooming in on the island within this image, you can see the island, you can see the hydrogen production line, you can see the wind farm. Again, these are all very early concepts, but the island exists, and we can model everything geospatially to scale. So as you're starting modeling the infrastructure, you can be confident that your analysis will be accurate and geospatially modeled correctly. So in summary, the complexities of the energy transition for the industry to decarbonize and move to new no carbon fuels involves new levels of engineering and financial complexity. So using a 3D digital twin approach can help you study these concepts in detail before any major CapEx commitment is made, to alleviate many risks at the early stage. Anything you design or simulate in the concept will ultimately become part of a sort of a dynamic data model, as opposed to static PDF documents or spreadsheets, which will have value as you build digital models over the life of a project. And we believe reuse and repurposing of existing infrastructure, as presented today in this, as engineered and conceptualized by McDermott, will have immediate CapEx and emission savings and ultimately reduce OpEx costs in areas such as predictive maintenance, as well as asset integrity. In the end, this will ultimately lead to vastly improved decision-making from the very beginning of any renewable project. And I'm certainly happy to speak with anybody listening about these concept projects or the Field Twin platform in general. Thank you so much for your time, and I appreciate you listening. Thank you.